Most 14-year-olds are busy navigating high school geometry, but inside a garage in Chicago, one teenager skipped standard flight lessons to physically construct a single-engine airplane from scratch. She spent her time poring over mechanical manuals for the Cessna 150, learning how to wire engine instruments and calibrate oil pressure by hand. Taking a machine you built into the air provides a specific kind of freedom. In that cockpit, you aren't just a passenger. You are the primary authority over the physics of the aircraft. But for Sabrina Gonzalez Pasterski, mastering the physical machine was only the beginning of the process. Eventually, the aircraft manuals and kit plane blueprints hit a limit. To understand the actual forces that allowed those wings to generate lift, she had to move beyond the engine and look toward the mathematical laws that dictate how space and matter interact. This transition revealed a gap in our understanding of the universe. When we try to combine the physics of very heavy objects like stars with the physics of the very small, the math breaks. We are currently missing a complete theory of quantum gravity. Resolving this conflict requires moving away from tangible engine components and toward a new mathematical framework for the cosmos itself. Today, Sabrina works as a theoretical physicist at the Perimeter Institute, an environment designed to allow scientists to pursue research that exists outside the standard paths of the field. Her office features an artwork based on the swirling style of Van Gogh. It represents her core question: if you look at the night sky, how do you encode the physical universe as a hologram? Sabrina is the lead of the Celestial Holography Initiative. Her goal is to take the holographic principle, a concept usually reserved for abstract mathematical models, and apply it to the real observable world. The celestial part involves looking at the sky and mathematically stripping away the cosmological constant, leaving researchers with an almost flat, easily calculated spacetime. The holography part suggests our three-dimensional gravity is actually a projection of a simpler theory occurring on a lower dimensional boundary. This concept mirrors the logic of the airplane manuals Sabrina studied as a teenager. A two-dimensional blueprint contains all the information required to build and understand a three-dimensional flying machine. Celestial holography suggests the universe works the same way. Everything we see in our 3D reality is actually encoded on a flat 2D surface at the edge of space. Solving the math behind a holographic universe is a sprawling, multi-generational task. Historically, physics has been portrayed as a competition between lone geniuses, each fighting to be the first to claim a discovery. Sabrina found that by prioritizing open dialogue over secrecy, her ideas improved faster. When you talk through a complex equation with a group, the feedback loop identifies errors that a single person might overlook for years. This approach shifts the goal away from individual prizes and toward the health of the research itself. It allows a physicist to become part of a long legacy of people trying to understand the fundamental laws of nature. Because if knowledge is power, then the most effective way to decode the universe is to ensure that knowledge is shared across the table, rather than kept in a garage.